those are also, those are also connected with artificial intelligence. So for this purpose, for the time being, we in around the world we have 76 billion devices, but most of them devices are based on the batteries. Those are powered with the help of battery, and because they are resistance dependent or capacitor dependent, so they need a power. And due to that requirement of power, they become
Sorry for interruption, Dr. Singh. Your voice is buffering actually. Can you check your internet connection?
okay. Let me check. Okay, I can try without my earphone. Maybe due to the earphone, there is a issue.
Yeah, you can check.
Hello. Hello.
Yes, yes, yes. Now it's fine. So
Now it is okay.
yeah, fine. You can.
Okay. Thank you. So, so there are a lot of devices nowadays in our world, but those devices are really bulky. As we connect the battery, we connect the capacitor with them, and they make the electronics very heavy. For this purpose, like there are two components: the sensors and the behind electronics. So sensor, in this case, those depending on the resistive base or capacitive base. In case of sensors, also we need to power them to get the output. But regarding the electronics, there is always you need to power the electronics with some battery. So we don't need to bother about it, but we need to bother always about the sensor that we have put directly in contact where from we are getting the signal. So let's say for this purpose, TNG and PNG are really amazing. They can generate the power and they can inherently give you directly signal without providing any batteries or capacitor. So I will discuss generally PNG and TNG in this case. And there are other type of other type of nano generators. Those are based on ferroelectric and magnetoelectric nano generator. They are also in demand nowadays. But I will discuss only PNG and TNG based. So how the triboelectric phenomena works actually. So we have this like we have this triboelectric series. In triboelectric series, we generally have a tribo negative material and tribo positive material. I have shown here few of the tribo positive and tribo negative material. So nylon is a tribo positive and PC is also tribo positive. Here P, PDMS, PVDF, these are tribo negative. So why these are tribo negative or tribo positive? This depend on the like they directly inherently like this is relative phenomena. So they are having different work function. According to that work function, they behave positive to another material. Let's say in case of PVDF, it is the fluorine, and fluorine is highly electronegative material, and it needs it wants a electron, so it becomes a highly electronegative. So due to which this is a tribo-negative material. In case of PC, the work function is very less. You can easily get the electron out of that as compared to the PVDF. So this PC become positive as compared to PVDF. So if you will touch them each other, they have a different work function, and due to that they have the different Fermi level. So due to which, if you will touch them, let's say in this case you can see the atom material A and material B, we are touching them. They have a different level of the Fermi energy, and so when you touch them, because of they want to when you touch them, they want to equalize the Fermi energy. So the electron from the positive will goes to the highly electronegative atom. In that sense, what will happen when the electron will jump? So that the material, let's say PVDF, here you can put the PVDF, you got the electron here on the surface. So that surface, the charge over that surface can be collected when you connect this material with the electrode. And you can, after separation, the material try to stabilize. In this form, what happens? So when you separate this material, try to stabilize, the electron goes back to its parent material. In this sense, what happens? We have a two type of piezoelectric and triboelectric. So in this case, I am describing this triboelectric. So what happens? There are this conductance current. You can say displacement current. So in this case, there are two type of current. One is the displacement current that generally flow through between the material when you are touching between them. There is a this current, and there is another current, that conduction current we say, that happens due to the electrons conduction, and this happens due to the electric field development because of charge separation happens. So there is the electric field, and due to which there is a this displacement current. So in this case, we have this displacement current goes through the material and air. So in case of triboelectric, the charge density play a very important role. And in this case, we can calculate the voltage with the help of this, the difference between these A and V, and there is a formula. With the help of that, we can calculate the voltage. Obviously, in this case also there is a displacement current, but the electric field is inside the material, and the current is always strong in case of piezoelectric nanogenerator. So this is the fundamental of this triboelectric nanogenerator and piezoelectric generator. I will describe how these work actually. So in case of piezoelectric, we already know. In case of piezoelectric, when you are going to press a particular material with some particular mechanical force, then it generates the voltage. But why it is happening? So we have this basic PZT material, lead titanate. So generally, the lead titanate has a structure like below particular temperature. It has a structure in tetragonal structure, and so because of this, it is having a this titanium ion not on the center. So generally, it is not on the center. So due to which, when you apply a force, it moves from one direction to another direction, and the dipole align in a particular direction, which create the charge on the surface, and that charge can be collected, and you got the voltage. So the voltage we got with the help of this, but the particular thing happen only below a particular temperature. When you go up the temperature, Cubic temperature, we got this Cubic temperature, you got the structure changes. In this case, what happens? The titanium ion is on the center, and now when you press it, it will not go because it is in stabilized condition. So the material should be in deformed structure to getting piezoelectric phenomena. So this is what we got in piezoelectric phenomena, and the main parameter in piezoelectricity is the D33. So we need to measure D33, and generally we have a really high D33 for. So what is D33 actually? When you are pressing a material, particular, let's say this material if you are pressing in y direction, then you will call it D331. If you are pressing it laterally, and also let's say x and y, then it will have a D31 and xz, then D13 like this way. So you got that way, the D31 or D32 or D33. So we have calculated, like we already have these values for the inorganic piezoelectric materials and organic piezoelectric material. The best piezoelectric material in case of organic is PVDF. So generally what happens in case of inorganic material, lead zirconate has a really high D33, and once you dope it with some other material, you can get much more higher D33 value. And if BATiO3 is also there, and in this case, what happens in case of BATiO3? We have a 193 piezoelectric ceramic in piezoelectric ceramic, and if you will do something, you can get much higher D33 value. But what happened in case of PVDF, we can't dope it. So what we need to do, we can reinforce it with different ceramic materials, and to enhance the D33. For this purpose, we need to make the composite material. So we have seen that in literature, people have reported the highest amount of D33, around 60, with the reinforcement of BATiO3 and also lead zirconate, titanate. But lead zirconate is not that good material, so because it is toxic, so we are not going to use in wearable and other devices. So why PVDF people are using? So PVDF generally found in four phases: alpha, beta, gamma, delta, and other phases. So what happens when the alpha phase is there? So in case of alpha phase, it has a it has a CH2 CF2 uh, see, it has a carbon chain on which it has a hydrogen and as well as the fluorine. So when it is having a alpha phase, it means it will not be in a distorted structure. Let's say in case of alpha phase, it will have a this type of structure. So the fluorine and hydrogen will be adjacent to not adjacent to each other. Let's say uh, on each carbon you have this hydrogen and you have this fluorine. So and here also again you have this fluorine and you have this hydrogen. So they cancel each other. But in case of delta you have this mixed one, and in case of beta you have a tetragonal completely not tetragonal. We call this all trans conformation. So we are here talking about the conformation. So alpha has a kind of trans-Gauss anti conformation, and delta has a mixed one. Gamma also have a mixed one, but beta has a all trans. So what happens in all trans? As the carbon chain you go, you will find that fluorine is always in one direction and hydrogen is in all other direction as on the adjacent carbon chain, due to which it make a particular dipole like this. So this dipole is really good in this sense, and this become a kind of a previously I have shown a kind of a tetragonal kind of structure. So not exactly like that, but like that, similar to that. So it has a higher dipole moment as compared to alpha, gamma phase, even more than the delta phase. So this people generally want this somehow in the PVDF material. So these are the FTIR and XRD of the pure alpha phase PVDF, this polymer, and we can see the similar we can see here this is the having all the alpha phase, and here it is the 840. I will describe it further because there is no, this is generally pure alpha phase, so we are not able to see the difference between beta phase XRD, beta phase FTIR. So I will describe it later because I have a beta phase XRD and FTIR as well, and also we need to get the D33 value approximately 20 to 33 or more than that to get the better output. And so apart from these beta phase enhancement and D33 value enhancement, you need to have a high electronegativity. So how you will get high electronegativity? Either you can get higher surface charge density, or either you can get a high electronegativity. So what you can do, we can reinforce with different materials that have a much more kind of fluorine. Let's say people reinforce PTFE. This has the PTFE has a fluorine, so it enhances the it enhances the work function of PVDF, and you got the higher amount of the uh, surface charge on PVDF layer as a negative triboelectric material. So that was the introduction that I gave about the PVDF and the triboelectric or nano generator material. What is our objective? So I will describe here the how the devices are developed and the structure and which material we have taken, and then I will show the characterization and electrical characterization, how we did the character, how we can do the characterize them for the particular application, because every application has a different requirement. Let's say there are some application in case of tactile sensing, you don't need to have a higher amount of voltage, but you just need a very small signal, so you can just sense it. But there are in some other cases, let's say in energy harvesting, you need to have a higher amount of the charge as well as the voltage. So in this case, we need to understand which electrical characterization need to be done for this purpose, and then we will understand how we can have different application on what application we have done in this particular lab. And also I will describe about the energy harvesting. I have shown some, I have some slides on the energy harvesting as well. So main objective of our work is related to contribution to the development of flexible electronics for future advanced wearable and AI IoT application. So obviously we will make a very small devices or wearable devices, and we have developed them. So I will show them. So particularly if we will talk about the device and their structure, so this is the TNG device. Nowadays in market you will find that I think the device generally are based on resistance, but in article of we have seen most of the TNG based device follow these structure. So most of cases even they are making with different technique. They are generally making film. So they are generally very thin films or like a thick film. They attach them with the electrode, different electrode, and they modify the film structure. And they also got the film with different techniques. So I will describe also those all techniques, and then I will jump to our technique. So in case of triboelectric, we have a four way of operation. You can have a contact separation. You can move the material like this to get the sensing application, and if you will move the material like this or each other. So we have here, we can see this is one is a triboelectric, one is tribonegative. So in this case, what happens when you touch each other, because of their triboelectric and tribonegative property, they generate the charge. But in lateral slide, you can slide over the each other. So because of the area is changing, so due to change in area, the surface charge density also changes, and because of that we can get the voltage. So another case, this is actually the contact separation mode is having two electrode, and another method and another way is that single electrode. So you can have obviously there is a one case, you don't need to use always this positive tribo material. You can directly use tribo negative material, and you with your hand, because your hand is highly tribo positive, it can deliver electronic, you can get electronic easily. So in case of PVDF, we have a tribo negative material here. You can push it with the your hand, like they call this hand tapping. So you can touch it with the hand. Also, you can generate the electrode. But obviously, with this single electrode case, even in this case, what happens? You don't need to put electrode on the active material. So the active material, let's say you have a PVDF, and this there is a single electrode. You can use any metal. So you push the active material with the metal, and on the metal, because obviously metal is gonna work as a positive tribo. In this sense, it's not a positive triboelectric material, but it has a much electron, so it can easily give electron to that negative tribo material. So on the basis of that, you can collect the charge. And another one is the freestanding triboelectric layer. So you can have these two tribo positive here downside, you can put, sorry, you can have a two tribo negative material in downside and one tribo positive upside, and you can again slide and freestanding whatever you can. It's almost similar to the lateral sliding mode. So you again you got that, because this difference, there is a definitely difference, because once this will come over this, the charge here will be very low, and here there will be a charge. So you can get this potential difference and measure it. So obviously you can get any voltage or any charge out of these four mode, but but the but the problem is that whatever device they are making, even in these four modes, they have only this film based device. So these are actually film based device. Also in case of piezoelectric, we have a three, like we can have different structure, and but the problem is that you need to apply the force in this direction. So in this case, the people generally shows this as a like two electrode based. You can push it from both sides, and you can get the output. even you can compress it like this way. In this case, you can make a cantilever, and you can push here the mass, and it will bend. You will get the output. So in this case, this is also the one way of getting the output. Another thing is that sudden, if you want the measure some sudden changes, let's say dropping a ball, or like pushing your feet on something, or we just in washrooms we just go and pushes the button to get the water out. So we can use this type of technique. They generally so. But again, the problem is that these devices are not suitable for wearable electronics, or even there are some cases in robotic application also these are not suitable. In this case, I am showing the how they are different between each other. I have already described in this case. So even they have developed a kind of a pattern over which you can touch, and in different case, we have seen this triboelectric shows better tactile sensing as compared to piezoelectric, because in case of piezoelectric you need to press it, but in case of triboelectric you just need to touch it. So the triboelectric is better for tactile sensing, and we will see how this work, how efficient this one in this case is. And we also see what purpose of this piezoelectric we will use in case of wearables. So the regarding the fabrication process, we have a lot of uh, techniques that people use to fabricate. So let's say we have this very basic solution cast process. So in solution cast process, they have a like what they do, they use the polymer, because I'm talking about the flexible electronics. So obviously we will talk about the polymer. So we have these polymers. They dissolve the polymer in some solvent that dissolve the polymer, and then they pour over a substrate, and they dry it with the help of solvent evaporation in a vacuum oven, and they got the solution cast film. They can use this for getting a thick film, and then they put the electrode over both sides, or whichever way they want to, what type of device they can put the both side or one side, and they use these devices. But this is very basic, and this is not much sophisticated. You will not get very smooth film, and even there, because of inside you are evaporating it, so there is a chances of getting bubbles spaces, or you can say there might be high porosity that can causes the easily breakdown if you are making much more thinner film. There another way is this electro spinning process. So this is the electro spinning process actually use the high electric field. You can have this metallic drum on which you apply a negative electrode against this polymer. So when you have a syringe, you fill the liquid inside this syringe, and because of this electric field potential difference, this syringe throw the liquid over this drum, and you got the very thin fibers over this film over the drum, and that drum can be like that drum can be removed, and you can get your film easily. So these they call it electro spinning based fiber, but obviously these are fibers in a form of film. So let's say you are making a very thin fiber out of electro spinning process, but you are collecting over a drum, and that drum is making those fiber, arranging them in a particular form of uh, structure. That again, it's the film. It's not a fiber. So they are getting the fiber, but arranging them in the form of film. And another thing is that you can press, like you can get any material, and even bulk material, and cut them, and you can hot press them. You still you can get the film. But obviously that film will have a, if it is not hot pressed very good way, it might have a uh, porosity, higher porosity, or the thickness. I think thickness is also the issue in this case. Hot pressing also, you will not get a very thin film, and obviously you need to apply high temperature in case of hot press, and that might destroy of structure, but that's not the big issue. The big issue in hot pressing is that you will not be able to get the very thin film, and removing that thin film from the hot pressing chamber is really tough task. So obviously, then there is another way you can prepare the thin film, uh, spin coating process. Spin coating, you put the polymer over a substrate and you rotate it at a high RPM to make the film. So this is also another way of making, and we have seen after blading. So again, this is a similar to solution cast process, but they use kind of blade, and then movement happen, and you got the film, and again evaporation happen. So these are some techniques. These are some techniques of making these films, and another way of making this triboelectric material, materials. There are one I came across when I went to this EMRS conference. There was a professor from Loughborough University in UK. They have shown their work on this deep coating process. So in case of deep coating, what they are doing actually, so this is what they do. They have a yarn actually. So the yarn could be of any nylon, or this could be wool. So what they do, they use that wool over which they first coat the silver. So they coat the silver over the yarn, and the silver is very, like, particle of silver are very small, so it can be bent, and like you can bend it like a uh, yarn. In this sense, what happens? So they make the yarn by silver coating as a electrode, and then they have this coating chamber. So this coating chamber is filled with the polymer, and they move this yarn through this polymer filled chamber, and the polymer is coated over this yarn, and inside part is uh, electrode. So this silver coated yarn become electrode, and over it you are uh, putting the polymer using this coating chamber. So you got this here, and the sudden, and at as soon as the yarn is coming out, you have this heating zone. So with the help of this heating zone, you evaporate the polymer, and you got the solidified coating layer over this yarn, and you collect it. After this, they generally do the knitting of this fiber, and they have knitted it, and they make a really big kind of mat. You can wear it, you can make something out of it, and that's good. But the problem again is this: once you stretch it, the polymer might get stretch out, because it's over the silver, so particles are there, they are not stretchable. So when you stretch it, the polymer may come out. So that's the problem, and it it has a break breakage when you stretch it. Another method of getting is a soft lithography. Like they use a substrate over which they have a this photoresistance material, and they use the UV light, and they can print different of these structures. So again, this is also planar kind of structure, and our main purpose was not to use this because of because we want to make a yarn. So this could be our suitable way to making a yarn, but obviously there is a one problem that when you stretch the material or somehow you rub it, polymer might go away. So that's the problem. So what is the solution for this problem? What is the solution of getting better wearable devices? And what is the solution that you can easily get the stretchable devices? You can bend it, you can like make it very big. Let's say in this case they could not make much more bigger yarn than 10 meter or 20 meter. They quote it, but obviously that has a huge problem. So what could be the solution for these all problems? So we had a one thing that we are doing here. So the thermal drawing process. So what is this thermal drawing process actually? So this in thermal drawing process, what we have, this process previously used for the optical fiber drawings. So those optical fibers, they used to draw with the help of this thermal tower, whatever we call it thermal tower. I have the structure of this thermal tower. I will show you in next upcoming slides. So we have, so what we do, we we need to make a preform, whatever type of device we want, and we put this over we put this preform over a particular furnace, and then we heat the furnace. And when you heat this preform, so this preform, like you can make any structure. You can see here, you can make any. So this is the cross sectional cut of this fiber. So you can make any type of uh, device, any type of structure using this uh, technique. So we have this. So you heat this preform here, and once you are heating, there is a chance of melting down. So how you will like you can use different. Let's say you have a same polymer, you can easily calculate the melting temperature, and you can easily get the necking. And after getting necking, you can push it with the help of gravity. You can push it, and in this sense, you will get the continuous fiber. But there are some parameters that need to be taken care. One is the viscosity, another is the drawing speed, how much speed you need to apply it. And also we need to use what speed you are feeding the this preform. So for this purpose, we need to understand, and also we are not gonna draw a single material. Let's say they previously in optical fiber they used to draw the glass ceramic. So drawing glass ceramic is easy in this case because they might be using single material, and in case of they can design with the help of that particular material by designing different structure of preform. See, they have developed really different structure using this system. So here is the fabrication of our device that we have developed using this thermal drawing system. I have a video here. I will show that video. So what we do actually, so I have described this thermal drawing process already. Sorry, the solution cast process already. So we have this polymer. So what we do, PVDF is there. We use the DMF. DMF is a solvent that dissolves the PVDF. So we dissolve the PVDF in that solvent and stir it for, let's say, 1 hour. Simultaneously, you put the SNO2 or any reinforcement, like you can use any filler to make a composite. So you can put any filler and with the same solvent. So both solvents should be similar, so they can mix. When you are mixing, there should be a good solution to get this film. So what we do, we use the similar solvent and we dissolve. We put the SNO2 here in DMF for 1 hour, also PVDF on 1 hour. We put this on ultrasonicator, or you can use the probe sonicator to make the good mixer. So after this mixer comes out, we mix both of them and put for 4 hours at 55 degrees Celsius. So when you put that 55 degrees Celsius, you will get a homogeneous solution. So once you got the homogeneous solution, it's not a solution, it's a quite mixer because SL2 will not dissolve it. So it's a mixer. So you got a homogeneous mixer and you pour this on a particular very big petri dish. We generally have these petri dish of 30 centimeter to 50 centimeter long. So we generally pour the material over here, and it depends on how much bigger preform you want. According to that, you can take the weight percentage. Let's say we are making 20 meter of fibers, so we can use like 20 gram or 30 gram of PVDF, and according to which we can use the reinforcement of material. And obviously, we generally take 70-30% of this solvent according to our measurement. So, and you can add the solvent when it is getting evaporized very fast. You can add the solvent further to get the better homogeneous and clear solution. So sometimes it might not be clear, obviously. So you got this solution cast film, and then you put this on in a vacuum chamber for 8 hours or 10 hours at 80 degrees Celsius, and you got after a self-standing film. You can wrap it around. Then we have this conducting polyethylene. So I will describe what type of structure we are getting for this fiber. So what we do, we got the conducting polyethylene planar film. We wrap it, and what we do generally, we make kind of, we cut this and fill inside a tube. We have a PTFE tube. We fill this cutting of this CPFE in CP4 inside this PTFE tube. So once you fill it tightly, you put this for consolidation. Like you want to make a hard code. It is a solid code. So once you consolidate it over around 240 degrees Celsius, you got a very solid rod. So it's a around 10 centimeter solid rod. Over this, we put this PVDF film. After cutting with a similar thickness, similar dimension, we can roll over this piece film over it. So this is a kind of structure you got like this, but because this thermal drawing process, because we are going to draw material thermal drawing process. In case of optical, they used to do for the single material, but here we are going for multi-material. So what we need to do, this is a PC polycarbonate. Polycarbonate is a highly, it's a kind of like for thermal drawing process, you need to have a material that are easily thermally drawable. Those are the thermoplastic generally. So polycarbonate is used as a sacrificial layer. So you need to wrap the sacrificial layer over it, and then you will got this type of preform here. Got this type of preform, then you will load it over the this tower, fiber tower. So the fiber tower has this furnace, and this furnace is there. It's a quite semi-automatic. I have a video here. I will show this video. So this is a quite semi-automatic. You will put over the furnace here. There is a like here around above it, we have a holder. On the holder, we put the fiber using some clamp, and that clamp can be moved with the help of your computer or PC. This preform will go inside the like this. This will go inside your furnace, and then you can heat it. After some time, you can start a heating. So we generally used 243 degrees Celsius to heating up this structure, CPE, PVDF, and this PC. So when you heat it up, you got the necking. So the problem is that how you will get the at what temperature you will get the, so at what temperature you will get the necking. So we call this when, so generally preform is like this. So you will make a hole here and put some weight over here, and you will you will get the necking here. So that as the polymer is melting, it will melt in a cone shape. So that cone shape is called as a necking. But the problem again is that you are using like we are using a multi-material. So at what temperature we will get that necking? For this purpose, we actually do dynamic mechanical analysis. So this is a thermal mechanical analysis in which we put the all samples and we heat it up. So we get the viscoelastic analysis of this. I will show those plots in further slides. So when you do those, you calculate the storage modulus as well as loss modulus. So once you calculate the storage modulus for the measure the storage modulus at 0 to minus 50 to 40 degrees Celsius or to 50 degrees Celsius for every material. Let's say we got the plot for a CPE, for storage modulus and loss modulus, for PVDF film storage modulus, everything we got. So these viscoelastic data is used, and then we merge the data plot in origin. We got a crossover point. So that crossover point between loss modulus and modulus for all the material, that particular temperature used for drawing these that particular temperature help you get necking. So after getting this preform, you put this and you draw it almost like 5 minutes or 10 minutes or 20 minutes. you got the drawn fiber like this. So you can see the dimension could be 1.25 mm, and even we have got 200 micrometer fiber, and very small, very thin fibers we have got around like 500 micrometers. So the reduction depends on how much you are giving. So deep preform, the thickness, diameter of your preform, and D is the diameter of fiber. So how fast you are heating it, and how fast you are drawing it. So V is the how fast you are feeding, and V draw is the how fast you are drawing. So this is the capacitor here. So in this piston, we have a roller. So we put initial fiber, as you soon get initial fiber, you roll it like this at a particular speed. That speed determine your fiber diameter. So when you are hitting a higher speed, your diameter will goes down. Also, you can vary it when you already prepare the preform. You can lower this speed with thinner fiber. So with this method, we have got almost 20 meter, 10 meter, or 30 meter long fibers. And that fibers is so good. I will show next slides. So this is our fiber tower. I'm drawing the fiber. So you can see it's visible.
Yeah, it's fine.
So this is the capacitance. So we are okay. So this type of fiber we can get using this thermal tower. It's a semi-automatic tower. So after this thermal drawing process, we need to do the characterization. We need to understand what type of fiber we have got, what is the structure of our fiber. So this is the small bundle of that fiber we got. It's almost around 1 meter. And to understand the structure of our fiber, we cut it in a angled cross section. So you can see this is the same image. It's around 1 meter. The scale is around 1 meter. So you can understand this dimension is 1 mm. So here we have this PC. As soon as like the structure is similar to what we got in preform. So we will PDF and we got the CPE here. Also, when you thermal draw, the main issue when you thermal draw, you are doing a heating as well as after heating at a 243 degrees Celsius, you are drawing your fiber, you are cooling as well. So crystallization also happening due to which you get your polymer get crystallized, and it has a higher amount of like formation of these spherulites. So we have got in our polymer, we got the spherulite in this sense. So these are this type of structure we got in our polymer when we remove the PVDF PC over it, and we checked our polymers, and the structure was like this. So the polymer become much more crystalline, and it has a higher amount of beta phase. So the struggle was getting a beta phase finishes here, because when you are stretching, it is a kind of you are doing a self pulling. So when you stretch, because in thermal drawing you are stretching, you got the beta phase higher, and also crystallinity is also higher. We checked with the elemental mapping how much reinforcement is there. It is homogeneously distributed, or sometimes it's not. So obviously, if your nanocomposite is formed homogeneously, you will get homogenized film in this fiber also. So after this material characterization, we comes to know that what kind of flexibility we have in our fiber. So what we did, we wrap this fiber around this Teflon tube. You can wrap this around Teflon tube, and you can understand how flexible these are. We also have this stepper motor. We can use this stepper motor to tap it almost 75,000 uh, cycles on it to understand how much how much cycles it can bear. So let's say with the 20 hertz frequency, in a 1 second you are tapping it at 20 times, and you we left it for 1 hour or more than that, but we could not get any crack in the fiber. So it was almost like 75,000 or more than that. So you can use these as a sensor by removing the outer layer. And so we have also used these devices in some particular application. We also did the material characterization with the XRD, FTIR. Also, this is the storage modulus and loss modulus, and we calculated the beta phase. So here, what we need to see. So in this case, as compared to pure PVDF, we can see the sharpness of beta phase is increasing. And again, we have also done the FTIR. Here, the case is very clear. I think it would be better if I could zoom it, but so that's okay. So you can see here, this is the pure PVDF that has been developed with the solution cast process, or after the thermal drawing. We can see when there is a no reinforcement, you have no pure PVDF, pure beta phase peak. But in case of here, you can see there is a clear peak. So the intensity is increasing for this 840 cent per centimeter peak. So that peak actually give you the calculation of higher amount of beta phase. So we calculated the higher amount of calculate the beta phase. We comes to know that there is a definitely enhancement in the beta phase, also enhancement in the crystallinity. And we did the DSC to understand the stability of this polymer. There is no like you are heating at 240 degrees Celsius, but after heating and cooling, there is no issue with the stability. The polymer is really stable, and as you can see, as we are reinforcing more amount of nanomaterials, we are getting more beta phase. And again, so uh, this is the measurement that we did for the understanding how much reinforcement we can do to draw the fiber. So the fiber, the polymer that you are making as a solution cast process should not be actually much rigid. If it would be much rigid, then you will not be able to draw it. So I was also talking about the crossover point between. So this is for pure PVDF, PVDF based material, not for the CP and PC. I should have shown this, but somehow I could not. So here, once we have seen, as soon as we are reinforcing more amount of the reinforcement SNO2, we are getting higher storage material. Sorry, higher storage modulus. So that means material is becoming much more rigid. Now it will be tough to draw this when you will reinforce. Let's say you are reinforcing 7% or 5% or 6%. You will able to draw the fiber, but eventually it will break. So you might get like 1 centimeter, like you might get 10 centimeter or 5 centimeter or maybe 1 meter, but you will not get 10 meter fiber, obviously, out of more reinforcement. So we also did the this XPS to understand what is the, like, this is a very, very basic. We do generally for to understand how the bonding is there in PVDF and SNO2, and this type of PVDF SNO2 is available in the inside this nanocomposite material. So there is another thing we need to check. So after getting higher beta phase, we already get as soon as we understand from the previous slide, you also need to understand the butt function, or like surface charge density. So how you will calculate the surface charge density. So we have this AFM. So AFM has another mode that we can call KPFM, Kelvin probe measurement. So with this Kelvin probe, we can calculate the surface like CPD, contact potential difference. So that contact potential difference can be helpful getting your work function calculation, surface charge density calculation. So we also did this surface charge potential measurement for the electrostatic simulation to understand how the material is behaving after reinforcement of this SNO2. So we did the KPFM. We come to know that the CPD has enhanced in a negative. So PVDF has this negative CPD, but after reinforcement, it has a higher negative reinforcement because of so the SNO2 is having a more electroaffinity as compared to like electron. It has a higher electron affinity, so it's sucking the electron out from nearby PVDF structure and making the film much more electronegative. So in this sense, what happens, it will become tough to get the electron out of this nanocomposite. In this sense, what will happen, the work function will increase. So obviously, I calculated the work function using this CPD, and with the help of, I used with the help of this PTIR tip of AFM. This is the platinum iridium conducting tip that we use to measure the CPD of this PVDF film. So what we did, first we measure with the help of gold. You can make a reference. You can use the PTIR tip to measure the work function of gold, and then you can measure for this different film. So the gold one will be standardized. You can calculate the PTIR tips work function. So we calculate the CPD of tip is around 5.2 electron volt, and with the help of this gold, and then we calculated the work function for this PVDF as well as PVDF SNO2. So there is a formula. You can easily calculate the surface charge density. So once you have CPD, you like this CPD you got, you can also calculate the dielectric constant with the LCR meter, and then D is the, there is a mode always. So D is the distance between the when you are measuring the KPF, measuring the CPD, the distance between the tip, that PTIR tip, and this sample is known as the this tip to sample delta height. They generally call it delta height. So you need to put the delta height here, and then you got the surface charge density. So as soon as you are getting a higher negative, higher CPD, you will get higher surface charge density on your negative tribo material. So that's what we did here, and obviously with the help of that, we also did the simulation. I have the simulation file, and then I can show that simulation file. So we calculated this, and then we measured, and we predicted that we can get the higher amount of the voltage with this structure, with this reinforcement. So after this, we did the electrical characterization, because obviously you need to know dielectric constant, because in previous slide I have shown that how we need to have this dielectric constant. Even the dielectric constant is increasing, but the CPD is much more dominance in this case. That's why we are getting higher surface charge density. So see, so LCR meter we used for this purpose. We have this type of structure of our fiber. So we wrap a copper tape over it for 1 centimeter, because if we will cut it and we will make a flat film out of this PVDF layer, then it will no longer be a device. It will be a film, and it will be useless. So here we directly measure the dielectric constant of this coaxial kind of capacitor. So we did the Z impedance measurement. We also did dielectric constant and 10 delta loss. And we come to know with the help of Z impedance measurement that it's a very linear kind of capacitor, and this the dielectric constant can be measured easily. And we got the enhancement in the dielectric constant from pure PVDF to reinforced PVDF around 27, and the voltage also enhanced. So we measured with the help of oscilloscope. We used the oscilloscope to measure the voltage. So how we did, we used the same device, the tapping device. The tapping device is having this PC tapper, and we put our fiber here and we tap like this. So in a particular frequency, let's say it has a 7 hertz frequency, we measure the voltage. So with the reinforcement, the voltage is definitely increasing, and we put the rectifier here. So you put the rectifier. Once we put the rectifier, we can calculate the uh, rectified positive wave. So we calculate the rectifier positive, and after this rectification, we also measure the power. We put the here resistance, and obviously the fiber has a different impedance. Every fiber has a different impedance. So we need to know the impedance at which we have a peak power. So we have this formula V square by Z. Uh, so in this case, that Z have a XL as well as RL. So those XL and RL should merge, like they should, there should be a kind of like they should be equal to each other. Then you will get the uh, peak peak power. This is the kind of we use in Thevenin theorem in electrical engineering. So with the help of that Thevenin theorem, we can calculate this resistance and Z impedance to get the peak power. So we use the same method, and we got the peak power around 32.11 microwatt, and it's a too huge. And as the reinforcement is increasing, the peak power is also increasing. And load resistance obviously will increase because this SL2 is a wide band gap semiconducting material. By removing this resistance, we can put the capacitance, and we can charge this capacitor using this TNG. So this is also the part of energy harvesting, how you can do the energy harvesting. So when you put the capacitance here, you can definitely charge it. So we put the different capacitance, 3.3 microfarad, 10 microfarad, and 100 microfarad, 470 microfarad. So in 100 second, 200, like we put this fiber for a long time and continuously tapping, like it was able to charge the capacitor, but the charge could not reach up to high voltage. It will take a lot of time. This is due to because the device also has an impedance, and also these capacitor also create a kind of impedance. So there is a particular limit on which you can charge. But obviously we have a charge. We collected a lot of charge. Like you can see, it reached up to almost 1 millicoulomb. So it's a huge in this sense. Energy dense. So energy also charged a lot. And another electrical characterization we use this metallized polypropylene capacitor. So generally people got okay. Sorry. So generally people got this type of rectified voltage, but they think that this is the DC voltage, but it's not, because DC voltage should be having a very zero frequency. So we get obviously that if you want a DC with the zero frequency, you can use this device, metallized polypropylene capacitor. So with the help of this time constant, as soon as you are hitting, like you are doing tapping, you are doing tapping, you can easily get the one time constant matches with the tapping, you can easily get the DC voltage. So we did this and we got the DC voltage around 15 volt. Obviously it will decrease. And then the sensitivity. So our application was in robotic tactile application. So we need to measure the sensitivity of the device because of this. So generally people measure the sensitivity in the linear form, and also they do this with as they apply the force, they got the voltage, and when they got the voltage, they plot it. So they got the linear form. But because I want to use this fiber in robotic application, so we need to understand if it is true or not. So what we started with the balloon. This is a Mylar balloon. So we use this Mylar balloon over the fiber. We connect the electrode to the oscilloscope. Here also we connect the oscilloscope. So we hit the balloon over this what we call this fiber. and we also swing over the fiber. So we got the, like, it is a really sensing. It's a so sensible that you are touching the balloon. It is a giving sharp peak. Also, you are going over. It is still giving the sharp peak. So it's highly sensible. But how much voltage it can sense? Sorry, how much force it can sense? Like you can apply like too high voltage. Will it still sense that, or it will collapse? So what we did, we used three type of different size of tapers, change the surface area, and this stepper motor is used because it can vary the force. You can apply the voltage, you can change the force according to the frequency. So I got this, and with the help of that, so with this force application, we come to know that this plot is definitely linear in case of voltage and force, but it's not linear in case of sensitivity and force. So what is the value up to which it can be a good sensor? So we did literature survey. We measured for different other articles. We comes to know that it is a very natural. It's not only in our fiber. It's a very natural for triboelectric devices. You have a particular threshold. After that, the device becomes saturated. You can't push much more to get higher voltage. So we also did this on our fibers. We come to know that around 20 or 30 it's okay, but above that it's saturated. You will not get higher voltage more than this. So definitely for those robotic application, generally it depends what type of robot you are going to make. So we were just making a robot for this continuum robot for collision detection in a pipe or whatever. So what we come to know that this is okay because we just need to 5 or 10 Newton voltage to under 5 or 10 Newton force to get the collision and to get the sensing property. So it is okay for our fiber. If it would not be okay, then we will optimize it in a different way. So what we did in case of application of this particular fiber, so there is a continuum robot. It's a kind of like like generally robots you have seen, they have a joints, they can move like this. They have a joints and they move their arm in different from joints. But in case continuum robot, there is no joint. These robots are actually continuous, like a snake or elephant trunk. So elephant trunk can bend from anywhere, and snake can also bend from anywhere. So these are used for, let's say, for different applications. These robots are used in particular pipes. They have a long trunk around you can say 10 meter, 100 meter, or 200 meter. You can push that trunk inside a pipe, and you can detect different metals with the help of this. Previously, they used to do this with a like a memester or resistive based or capacitive based sensors. But because of again we need the battery, and you don't know what is the inside that also the what time it will take. So battery might drain inside this pipe, like it might take a lot of time. So you need to charge the battery again and again. So that is the problem. So we solved this problem using so this is the basic structure, CAD based structure we made for this has a motor inside it, and it has a kind of trunk, and we put our fibers here because see, in case of elephant trunk, they have a skin for the sensing. So in the case of snake, the snake can sense from anywhere from skin that they are being touched. But in case of fiber, if you will push it, and you will think that it will attach to summit, and you are pushing the trunk inside, and still you are not getting any signal, and you are pushing, then trunk might get destroyed. So for this purpose, you need to put say some sensor to get signal output. So we put our fiber here, here, and here. So after putting the fiber here, we can push this trunk inside a pipe, and you can, whenever there will be a collision, you can understand it. So we tested this, and we got to know that with a particular when we are putting this like, so what we did, we put this here everywhere on this TWS, and try to touch with our hand to test it. So we got the signal that when someone is touching, we can easily detect it. So for this purpose, we use the Arduino. There is a microcontroller that we use, Arduino and resistance and this type of structure electronic we use to connect with it. Obviously, electronics you need to use the charging, but this electronic will be connected. See, this electronics will be here, not in the trunk. So in the trunk, fiber will be here, and the wires that are connected for movement, those are connected with the stepper motor, or you can use, like some people use the hydraulic system to move this trunk of this container robot. So we tested over it, and it was perfectly worked. So perfectly worked with the TNG systems. And I don't have the video that we did real uh, uh, demonstration of the device. I should have downloaded it from my paper, but sorry for this. I forgot. So we did this also in the real scenario. We put the long trunk and we pushed the inside of pipe, and it was doing great job because we simulated like kind not we simulated real scenario in real time. We put different material. Let's say we put the metal, we put the somewhere polymer. So it was giving a different voltage on different positions. As that we can measure the trunk length and the at the position detection we are getting. So on the basis of that, we can know where the collision is happening and where is the problem. So that we did with the help of this fiber. So this was our first fiber. And then there is another fiber we developed, the piezoelectric nanocomposite fiber sensor, uh, wireless monitoring of physiological signal. So the previous paper has also been published in ACS Applied Material Interface, and this paper also been published from our lab. And I will describe this. So we use the previous structure was very different. Like it was a coaxial core, and it was a TNG device. But here I am describing the next one is a piezoelectric nanogenerator. So in this case, so we have this the same method we use to prepare the film, because eventually we need those active material as a film formation, and you make a preform in a different way. So what we do, we hot press, make a strip, like we make a kind of seat. So this CPE is actually conducting polyethylene. So this is we use as an electrode, and SEBS is a butylene rubber. So this rubber is actually used for enclosing our device. So previously TNG doesn't need to be enclosed. Yes, you can enclose with something else when you are using, but for that time we didn't use any enclosement. But in this case, because we want to make a two electrode in this case, so they should be connected to each other, and it's not a coaxial fiber. So here we have we enclose the active material and we make a full device. So we have this electrode, we have a conductive polyethylene as an electrode, because you need to apply the force this way and you get the output. And this is a piezo layer. So this is the piezo layer here, and you enclose with the SCBS, the rubber. This is the really flexible, and it can be easily thermally drawn. So with the same method, we thermally drawn this, and this is the structure. After getting this, you can see it's a 5-meter long fiber, and it's a very small. It was around 600 or micrometer thick. So this dimension was 600 or 500 micrometer. So this was very thin, and then we layer this around the Teflon rod to understand how flexible it is, and we can make a net out of it. We also weave these fiber in a kind of like textile, also in different way. And again, we did the electrical characterization. I am not showing here the material characterization. We did the same way, the FTIR, XRD, and obviously it's a thermal drawing process. You are stretching, so there is a self-pulling. With the self-pulling, you got the dipole alignment, and you got the higher beta field. So this is the our structure of our PNG device. So this is the, consider it as a PVDF layer, where when you are pressing it, let's say you are applying a force. So dipoles, like here, dipoles are arranged in randomly. When you apply force, you got the dipole in one direction, and you apply more force, more dipoles are arranged, and then you can collect this, and you remove the initial position is reached. So we got the voltage very less as compared to trigo. Obviously, piezo gives you less voltage as compared to trigo, but the sensitivity is higher in this case. So we use this for the physiological application. In this case, what we did, we also measure the open circuit voltage, short circuit current, and the peak power. Here we measure the peak power. It's around how much we got, around 5.5 microwatt. And we also check after 6 weeks how much it is retaining. So the performance is equivalently good, not much degrade. So for the wireless monitoring of biomotion using a single fiber sensor, so we need to use what we did here. So we can put our fiber everywhere, because this is a triboelectric fiber, so you don't need to touch it every time. You don't need to take this. You can push it when there will be any physiological motion on your body. You can detect the signal. So for this purpose, we use this device. So let's say we put here on the finger, we can tilt like this, and there will be a stretching due to which it can give a voltage. So how we did it? So we stretch at a different position on our here, and also on back side of the neck. We put this fiber, and for this we use a piezoelectric fiber, our fiber, and then we have this microcontroller, again the Arduino, and we have system inbuilt Bluetooth system in the Arduino. We can directly connect to the our laptop or computer, and you can get the output. So you can see when we are doing like this, we can get the output, and at 95 and 45, you can get the different output. So you can measure the how the physiological motion is happening, and these motion are actually done for those paralyzed people. So what they do for paralyzed people, there are devices. They put the device here on the particular fingers, and they ask them to move their fingers. So on the basis of that, they can check how which finger is having a better output, which finger is working better, and which is not working, and what is the like there is always optimization. What is the issue with this motion? You put these fiber for like 1 month, and in 1 month they can detect where is the issue. In 1 month there is any irregularity. So also they put that on here, and they try to measure the motion, and obviously there's a with the different angle, the motion is always different. So in this case, we physiological sensing we did from the this your as your heart also vibrate because of this systolic like there is a contraction and separation in your heart because of heartbeat. So you always get the, as the heart is beating, same force is applied, same the blood is flowing in your veins. So according to same like what I can say, same frequency, your veins also vibrate. You have those. So we try to put this our fibers everywhere where we can feel this beam vibration. So we put our fiber and we measured everywhere. So we got to know that it is very suitable for physiological sensing, and we are getting. So I can show this video how we did it. So we put this here. We are getting the data. So this is very cheap and very scalable thermally drawn fibers. So we can get rid of those advanced systems and we can make a cheap systems. So these could be accessible for everyone. So that's what we can see. So further after that we also make a hybrid nano generator. So after piezoelectric and triboelectric, we also combine both of them. So how we combine them? Because the structure is very different, you need to have both triboelectric and piezoelectric phenomena. So there is always issue with the it's a very basic thing. So again, we are going to use the thermal drawing for this purpose. We are using SEBS for flexibility that previously we have already used. And obviously for novelty purpose, you need to search for the other nanoparticles to get higher like surface charge density on PVDF. So what we did again, so we use different nanoparticles in PVDF, and we did the same thermal drawing. Also use the butylene styrene rubber. So the working of this is very different from previous device because this device is having both phenomena. The structure is also very compact and the making it is tough because see there were only two, and so inside a particular structure we are also using SEBS layer here, and inside that SEBS layer there must be a gap for triboelectricity. So for this purpose we used this structure, and I can show you how this works. So when you apply force, they touch each other, you got the triboelectricity, and you apply further force, you got the piezoelectric phenomena, and then you separate it, you got the recovery, you got the like initial position. So that's way it can work. So this has a both triboelectric and piezoelectric phenomena touching each other. Then you are applying further force. The force is there. It is stretching the other triboelectric material or piezoelectric material. You got the output. So it should give higher amount of output as compared to the TNG or PNG. Obviously, so let's see what will happen. So again, the same method we use developing the film, but obviously the stacking, there are a lot of stacking in this case. Similar process we use for that we use for PNG. So here we have a many seats. We have this SCBS, we have a CP, two electrode, because again we are making a two electrode device, and then PC. So PC is a positive tribo material, PVDF is the negative tribo material. PTF is making a gap inside between. PTF is not thermally drawable, it's a very hard and rigid, so we need to remove it somehow. So what we did, we got press them, and we got this type of a structure. So this is the HCPS layer, outer layer, and in between you got this. But there is a PTFE, so there would not be any gap. Once not be any gap, you will not be able to get the triboelectric property. So we remove the PTFE, and you got the gap. So this is the gap. Now we will thermal draw. So we put this again here on the furnace, and we thermal draw using the same method. But there is a one problem. Whenever we were drawing it, the gap was not there. So those each other were collapsing to like those, because for tribo we need a gap, so that gap should be made all over the fiber. If it is not there, then it will be useless. There will not be even PTNG or like TNG or PNG device mess. So what we did, we have a we have got idea. We can blow the air inside. So what we did, we got the pipe, and with the help of this with the motor, we try to flow the air. So we have this pipe, we put the pipe inside the preform and we flow the air inside it and then thermal drop. So very little amount of the air we flow, and then somehow many trials we did, almost like 7 to 8 times or more than that we draw. Then we got the fiber. So we got almost 15-meter long fiber, and this was remarkable in our case because this was most sophisticated thermal drawing in this case as compared to PENG and TNG. And still we got it, and we got the really good structure. The flexibility was really good. And so we need to measure, we need to understand what type of structure we got. So this is the PC CBS layer. We got this structure from laser scanning confocal microscope. So because whenever we put PM, this used to collapse because of vacuum. In SEM, there is a vacuum chamber. So we try to get this structure out of SEM image, but we never get it. So it was collapsing each other, and we were thinking, okay, then we are not getting the fiber as we are thinking. So what we did, we used this laser scanning confocal microscopes. So obviously you can understand here we have a CP layer, also here CP layer and PVDF and PC, and this is SCBS layer. So we got the finally our fiber. We also want to understand graphene nanoplatelets are present in our nano composite or not. So what we did, we reinforced. Oh, sorry, we did the TEM. We cut the polymer film using a laser cutter. We very thin film they cut and they put in on a sample holder, and then they measure. We got to know that yes, obviously the GNP is reinforced perfectly, and it's a good film. So further, we did all the characterization that we generally do for the other measurements. So enhancement in the beta phase, crystalline enhancement, it's always there. We will definitely get. And dielectric measurement, we also did the dielectric measurement for this purpose. And like you can see, the enhancement is higher because of graphene nanoplatelets are better for better way making composite. Also, they have a higher interfacial interaction with PVDF because of carbon and graphitic structure. It got a higher dielectric constant as compared to previous SNO2 and also this another one. And we also come to know that there is a very less difference in the dielectric loss, so it's good. And again, we measure the voltage and short circuit current. So you can see the voltage and the short circuit current has increased in this case. So what we come to know that the voltage for in this particular sense, we can see that it's a 32.6 volt. So you can see the coaxial structure was having much more surface area, coaxial structure, because it was a diameter, and but here we have this kind of flat inside this SCBS enclosed. We have a flat, so this area was very low as compared to this coaxial one. This still it is giving really. This was due to the both trivoelectric and hybrid, trivoelectric and piezoelectric one. So we got higher voltage, like it's a too much. And in case of PVD, pure PVD, we got even almost 50% more than the coaxial, and pure piezoelectric. Pure piezoelectric was very low. So this is enhancement is really like it was remarkable for our case, like with a very small system, very small thickness, very small what we call surface area, we are getting really good output. And we measure the power. So we got the power density around like 266.27 milliwatt per meter square. So we use 7.1 centimeter length of the fiber to measure these all characterization. So we need to understand how the coupling is happening. So obviously, someone can ask, okay, so what is the triboelectric and piezoelectric, what is the triboelectric piezoelectric percentage of like contribution toward the both hybrid output? So what we did, we get this PVDF layer out of it, and we measured the triboelectric and piezoelectric voltage. So obviously, piezoelectric is always less, and triboelectric is this. And when you merge, when you put them in a single system, they enhances the voltage really high. So this is not because the addition. This is because on the surface, the phenomena that are occurring is that triboelectric is a faster than piezoelectric. So, but what happens when dipole align in one direction because of force, piezoelectric surface charge is already there, and the synergetic effect after each cycle happens, and that synergetic effect also pushes much more charge out of polymer layer and give you higher voltage. So for fiber durability, what we did, we put the fiber for we use the simple, again the stepper motor to measure this, how long this can give a regular output without degrading. So around 75,000 tapping, we saw that it's still continuously giving same amount of the voltage, and even it's an increase of the charge is easily getting accumulated when you are pressing at a high speed. The charge is still there, so it also multiplying much more output. The surface. When we saw the untapped surface, untapping surface, after tapping, there is nothing issue with the material is okay. So we can do it after 7,500 tapping. We can use like 10,000 tappings or more than that. Like it's a two use. You can use it for 20,000, 30,000. There is no issue. So we also did the measurement in salt water. We put our fiber inside salt water and then tap it. And obviously, it was after removing this, we are getting the good output. And we also put this in a drum type, this washing machine, and roll it almost 4 hours, 8 hours, 12 hours. We got to know that there's no much impact on the performance. It's quite good. So we can use all like in very rough, tough condition. So this is the real tile-based system. This fiber can be knit in the form of even very suitable textile, where we can decrease their height, and we can wash those textile. We can immerse those in salt water. So that's not the issue. So we also made the, and we also use the and capacitance charging and LED charging to know if it is also used for the energy harvesting. But for application we use, and we many LEDs also to understand if it lighting up these LED or not. So obviously this fiber was really fantastic and it works, and energy storage is good. And further, we also use this fiber for biomechanical stimuli. So what are the biomechanical stimuli? Again, the same way we want to use these for obviously because of their textile thing, we want to use them. So we need to measure the muscle motion, whatever you are making, the muscle motions, your blood construction, and those things you are using. So you can use this fiber to test those things. So we put this at every point of every joint, wherever this, let's say, elbow, finger tips, and waist, everywhere and even on the knee bending. So we put this everywhere, and we are getting really fantastic output. And this is sensing so accurate. They are suitable for the physiological or biomechanical devices. Like they can be used in place of very sophisticated devices. So we also did the physiological monitoring. So in case of physiological monitoring, what we do, like I have already described why physiological monitoring is already important, because it is better to like you should know the abnormality. Every person should know the abnormality that is happening, and before the like before getting serious. So the serious issue should be prevented. So for this purpose, we can use these fibers in place of these very sophisticated devices, and these fibers are cheap. So we want to also understand this because of biomechanical. In previous slide, I shown the biomechanical uh, placing, and we got the output. But again, as similar to the PNG device, we also measured the physiological measurement for this hybrid one. So that's what I was talking last time. So this heart heart contraction and relaxation. So they call this heart contraction as a systole, and relaxation as a diastole. So systole and diastole happening inside your heart actually push the blood out of it and inside it. And due to this, the vein have a contraction and relaxation also at the same frequency. So you can put you can measure those any issue inside your heart. Let's say you put your device for 1 month, you can check in 1 month, or even at night you're sleeping, you can understand what is going on with your heart when you are sleeping. So people can use these, and nowadays people are using these devices. Those devices are really costly. We can use these fiber-based devices in place of those. So we also measure this. We put the fiber here on this tape. This tape is, I think, it can be bound around this wrist, or it can be put on the near the vein. So this way, it can, when the systole or diastole is happening, contraction and separation, like contraction and relaxation will happen. So piezoelectric as well as triboelectric might work. So piezoelectric, because inside part, so because of skin, it will not sense the triboelectric phenomena. It will, because inside it has both triboelectric and positive, tribonegative and tribopositive, due to which it will get, and it is a much more efficient as compared to only PNG. So again, we did the same thing with the Arduino, and the same system we use, and there is a one open access software that we can use from. So they actually filter the exact data to get the equivalent this pulse rate or respiration data. So what we did, we put the fiber on different places, again the same way. So we put on the carotid, coronary, and then we got the data. So we got the data, and it was really better than our previous fiber, and this is the improvement that we have done our system. So you can measure, you can see the video again. Okay, I can play this video again. So this is like we are measuring here. So further muscle activities, like after measuring those veins, relaxation and contraction, we can also check the muscles contraction or relaxation. So we put the same strap of fiber here, and the person asked to bend the his this vest, and then muscle contraction and expansion is happening. On the basis of that, we can measure what is going on. If there could be abnormality, the person will bend the very different way. So what they do actually in this case, so they actually do the optimization for real, like let's say we have this available devices, we will get the data, similar data for a healthy person. So healthy person, we will store the data from the healthy person. then there will be another person, those who are facing a problem. We will also put that device along with this, and they will we will collect the data, and then we will with the system, electronic system that is working there, will compare this with the healthy person or healthy data, and then it can easily track what is the issue with your arm or with your contraction and relaxation. Do you have any muscle issue or not? That's what purpose we can use. So the person was asked to bend it at a different angle, different frequency. So we got the performance was changing according to the different angle, different frequency. And also we asked him to lift a different weight at different angle. So on the lifting different weight, we have a different different performance, different voltage we will get. So on the basis of that, there is a variety of data. Like it's not kind of it's a giving only on and off. So it has a multiple states. So you can check those multiple state, and you can make your device on the basis of this system. And like you can train the AI system on the basis of these multiple data, lot of data, and that data can be used to track your abnormality in human body. And this is for the future AI systems. So summary I will summarize here. TNG and PNG are future for wearable and artificial intelligence, and thermal drawing is making this device efficient for wearable AI and IoT. So I would like to thank you, and it will be great to if you have any questions. Hello.
Yeah, in audience, if you have any question, you can ask. So I
Hello.
think there is no question from audience side. So thank you, Dr. Singh, for your nice presentation. So it will definitely help for our audience. So thank you so much.
Thank you. If they have any question, they can email me, and I think it was a good like if these are devices are really good. If they have any question, they can ask me later.
Yeah, sure.
Okay, thank you so much.
Thank you. So now you can log out your screen. So dear participants, thank you for engaging this lecture. So now we we are ending the meeting for all, and we will soon resume this MTP with another interesting session at tomorrow 9 a.m. Morning. So thank you so much for your active participants. Thank you.